What you're looking at now is an artificial neural network, or ANN, a simplified mathematical abstraction inspired by biological neurons. Just as the brain uses billions of interconnected neurons to process information, artificial neural networks use layers of artificial neurons to learn patterns in data. Let's walk through this network step by step. First, the input layer, the blue ovals labeled X1, X2, X3. These are the artificial equivalents of dendrites. Each input unit receives numerical data, just like dendrites receive signals from other neurons. In practice, these inputs could represent pixel intensities in an image, test scores, blood pressure readings, or any measurable feature. Next, we move to the first hidden layer, shown here in pink, with units labeled H11, H12, H13, He14. Each of these artificial neurons performs a weighted sum of the inputs it receives, followed by a nonlinear activation function. This mimics what happens in the biological soma, or cell body, integrating incoming signals and determining whether to fire. Each connection is associated with a trainable weight, analogous to the synaptic strength in biological neurons. Signals then pass to the second hidden layer, the green units H21 through H24. These neurons take the output from the first hidden layer and process them in the same way, computing a weighted sum, then applying an activation function. You can think of this as information flowing down the axon, being transformed at each step. This layered processing allows the network to extract increasingly abstract features, from raw signals to high-level representations. Finally, the signal arrives at the output neuron, labeled Y in orange. This is the prediction or classification result, like recognizing an image as a cat, estimating a house price, or detecting diabetes risk. Just as synapses at the end of a biological axon transmit information to the next neuron, this output can be fed into another system or interpreted as the network's final decision. Throughout the network, learning occurs by adjusting the weights on each connection. This is analogous to synaptic plasticity in the brain. The network learns from data by minimizing an error function, updating weights through backpropagation and optimization algorithms like gradient descent. Let's revisit the biological parallels. Inputs dendrites, hidden neurons soma processing with activation, outputs axon firing a signal, weights synaptic strengths, learning weight adjustments just like synaptic plasticity.